Welcome to This Explainer. Today, we're taking something totally ordinary, an everyday object, and, well, we're subjecting it to some high-stakes science. We are deconstructing the baked potato. But we aren't just talking about a simple recipe today. No, we're looking at the precise structural engineering and the thermodynamic principles required to construct an absolute culinary masterpiece.
Think about your own experiences for a second. What actually separates a sad, soggy, lukewarm potato from a structurally sound American steakhouse masterpiece? Why does one feel like a dense brick while the other gives you this brilliant interplay of fluffy starch, melted fats, and crisp, cold toppings? It's not magic, and honestly, it's not even just about the quality of the ingredients. It all comes down to precise thermal sequencing. To figure out how this works, we're going to follow a pretty strict scientific protocol. We'll start with the potato matrix problem, move right into protocol alpha, the emulsion, and protocol beta, the lipid shield. Then we'll hit protocols gamma and delta, and finally look at the main counterargument to this whole method, the homogeneity approach. Okay, let's dive right in. Section 1, the potato matrix problem. Basically, we're looking at a huge thermodynamic puzzle of moisture and temperature control here. A baked potato isn't just a vegetable. It's this incredibly delicate architecture of gelatinized starch granules that are just waiting to either be perfectly coated in fat or tragically ruined by water. The whole journey starts at exactly 205 degrees Fahrenheit. That's 96 Celsius for the metric folks. Why this number? Because the data shows this is the exact temperature required right at the geometric center of the potato. At this precise thermal threshold, the starch granules inside have fully gelatinized. They are swollen, fluffy, and primed for manipulation. If you pull it too early, the starch is way too rigid. Pull it too late, and you completely lose your structural integrity. The absolute second that geometric center hits 205 degrees, our mission begins. Section 2, Protocol Alpha, the emulsion. This is where we initiate the steam purge and apply our very first element. The technique here is absolutely critical. You've got to slice it open and literally push the ends inward. This action fluffs the interior and, most importantly, vents out all that trapped steam. And while that inside is still blazing hot, hovering right around 200 degrees, bam, we introduce butter. Now, scientifically speaking, butter is a water and oil emulsion. The intense residual heat of the potato instantly breaks this emulsion, which allows the rich milk fats to perfectly coat those swollen starch granules we just talked about. It adds immense richness without turning the potato gummy.
Which leads us to Section 3, Protocol Beta, lipid shield, and establishing our hydrophobic barrier. This right here is where we separate the amateurs from the thermodynamic engineers.
The whole concept of the lipid shield is just fascinating. Instead of just piling all our toppings on at once and crossing our fingers, we are purposefully constructing an impermeable sheet of dairy lipids. By dropping a high-fat shredded cheese, think a sharp cheddar or a Gruyere, directly over that steaming buttered starch, we are forging a literal shield. This barrier will physically prevent any water from saturating the potato matrix below.
The physics at play here? Totally brilliant. Your standard cheddar cheese has a melting point of approximately 120 degrees Fahrenheit. But remember, the residual thermal energy of our freshly buttered potato is still pumping out well over 150 degrees. That massive temperature differential is exactly what we want. This upward transfer of thermal energy just obliterates the cheese's melting point. As that heat rises, the casein proteins in the cheese completely break down, and those dairy fats just flow together. They interlock seamlessly to form a continuous, impermeable, hydrophobic sheet right over the exposed starch. The base is now entirely sealed off. Moving right along to Section 4, Protocols Gamma and Delta, introducing the upper layers and the cold suspension. With our lipid shield securely intact and completely hardened against moisture, we can finally introduce the highly unstable, water-heavy, and really delicate upper layers. We have to execute these final two protocols in a very strict sequence. This order is non-negotiable if we want to maintain distinct structural integrity and preserve those extreme temperature differences from the top layer all the way down to the bottom. Protocol Gamma brings us to the sour cream. From a scientific perspective, sour cream is a fermented dairy product, packed with a highly significant amount of water, specifically whey. If you were to drop that straight onto naked potato starch, disaster. The starch would act like a giant sponge. It would just absorb the whey, rendering the entire potato a soggy, lukewarm mess, and rapidly cooling the dish way down. And this is exactly why the shield method is genius. Because we laid down that melted fat layer first, the lipid shield physically kicks back the way from the sour cream. The fats act as an absolute brick wall. As a result, your sour cream stays perfectly cold, totally intact, and quite literally hovers, suspended safely above that hot interior. You get blazing hot starch on the bottom and cold cream isolated right on top.
Finally, we hit protocol delta, the oleums, so your green onions or chives. These guys possess incredibly delicate, volatile aromatic compounds. By putting them at the absolute top of our construction, literally as far away from that 200-degree starch as humanly possible, we stop the potatoes' residual heat from cooking them into mush. This perfectly preserves their sharp, astringent crunch, which you absolutely need to cut right through the heavy lipids sitting underneath them.
So let's take a step back and look at the whole engineering schematic here, specifically focusing on the thermal states. Down at the base, you've got butter acting as your emulsion coating at a blistering 200 degrees. Right above that, the cheese forms our hydrophobic barrier, melting at over 120 degrees. Sitting safely on top of that shield is the sour cream in a cold suspension, and the raw, cold alliums cap the whole thing off. It's a literally perfect gradient of temperature and texture.
But, as impartial reporters of culinary science, we have to look at all the data. That brings us to Section 5, the homogeneity counterargument, sometimes referred to as the Red Team report. There is a completely different school of thought out there that challenges this entire layered, shielded architecture. Plenty of chefs play devil's advocate here. They argue that constructing these highly distinct, impermeable layers actually ruins the eating experience. Why? Well, because the lipid shield is almost too effective. The toppings have a real tendency to awkwardly slide right off the potato when you try to take a bite. Instead, they propose a twice-baked or homogeneity approach, where you simply mash the butter, the cheese, the sour cream, and the hot potato flesh all together at the exact same time. The crucial thing to grasp here is the completely different philosophies at play. The lipid shield method is inherently geared toward that classic American steakhouse presentation. It is all about high stakes, extreme physical and visual contrast, hot against cold, rich yellow fats against stark white cream. The twice-baked method, though, it completely abandons contrast. It goes for a unified, homogeneous matrix, prioritizing holistic flavor integration where literally every single bite tastes exactly the same. Both methods use the exact same raw materials, but the thermodynamic philosophies are worlds apart. So, as we wrap up this explainer, I want you to think about your own strategy. The next time you step into the kitchen and pull a 205-degree potato out of the oven, which structural engineering philosophy are you going to deploy? Are you a precise shield builder chasing extreme contrast? Or are you a holistic homogeneity masher looking for absolute integration? The science is completely in your hands. Thanks for joining me on this explainer.